Okay, so this is the third handout of three to start off the chi-square distribution discussion topic. Uh, we're going to go ahead and take a break from the chi-square stuff for now and go back into two-way tables, contingency tables. We have three total chi-square tests, and we've already got one under our belt. Hopefully you're pros at it by now. It's a pretty simple procedure. Just needs some practice. And we're going to have a handout which will combine all three of these for homework, and it'll be due Friday this week. So far we have one test done. That's the goodness of fit test. We have two more pending. The chi-square test for homogeneity. So to test to see if different populations or different types of populations have the same type of distribution with respect to some variable. So there's a variable in question or a variable of interest, multiple populations. Do these populations look like each other regarding that variable? That's the test for homogeneity. So are these essentially homogeneous populations is the question. And then the third type of test is a test for a relationship between variables, some sort of association uh, or independence. So are these variables associated or are these variables independent of each other? So it's called a chi-square test for independence, or also known as a chi-square test for association. They refer to the same test. So you'll see two more chi-square tests. And this is before that. So we're going to go over the mathematics of contingency tables and graphical stuff too. So how to graph the distributions on a contingency table. So we'll get into specifics on this one today. So a two-way table or contingency table, two different terms which refer to the same thing. So they're synonymous. So I like to call them contingency tables because it makes me sound smarter than if I were saying two-way tables. So anyway, it's a tabular display that organizes data according to two categorical variables. So you can think of them as two categorical variables, or we can also think of them as one variable and multiple populations. So either way. So we talk about two different types of sub-distributions within this big two-dimensional joint distribution. So there are two variables we think, but what we do is we think uh, single variables at a time, and we either think of single variable distributions done conditionally or done marginally. So marginally would refer to like the end or the totals, the total columns or the total row for this table, because it's a two-way table. Some are vertical, some are horizontal. So you have rows and columns. And conditional talks about the what looks like a marginal value, but given a specific condition for the other variable. So if I were to read that straight, a conditional distribution is a variable or the conditional distribution of a variable describes all the values of that variable among individuals who have a specific value with respect to some other variable. So we think of a contingency table as graphing data over two different variables. So these are individuals for the most part, objects, whatever, and they're being categorized with respect to two variables. So let's say age category and then also income category. And so one dimension of the table, the columns cover the age categories, and then the rows, the other dimension covers the income categories. And then, so what we do is we go ahead and set a constant value for one of those. So let's say for this particular income bracket or this particular income category, what's the distribution of age look like for that one income bracket? Or maybe for one age bracket, one age category, what does the distribution of incomes look like? Those are called conditional distributions. Marginal distribution is just answers the question, what does the distribution for one variable look like altogether for everybody? Or what does the distribution for another variable look like for everybody? So those are marginal. So simply put, if I'm looking at number one, this thing talking about the total for this is type of protein in a particular order of food. So the type of protein or the lack thereof, this is a marginal distribution. If I look at this way, and that's not including the total, it's just these three numbers because there's three categories for that one variable. If I look at, I think this is 1, 2, 3, 4, 5 categories, and I plot this as like a bar graph, that's another marginal distribution. So those answer questions like, well, what does the distribution of the food type look like? Or what does the distribution of the food protein look like? All across the board. So those are marginal distributions. A conditional distribution looks like this. So out of the orders that were fast food only, so out of the fast food orders only, what is the distribution of protein? looking like for just the fast food items. That's what we call a conditional distribution, and this plays exactly like a conditional probability. So under the condition that we're ordering fast food, then what's the probability of this, this, and this? And each individual category has its own probability, and those probabilities are proportions. So those are conditional distributions. So we'll go ahead and read number one, get some context in here. Amy's Joe's immediate supervisor, and Amy usually works through lunch. She likes to ask anybody in the office that is headed to lunch to pick up some food for her. Joe has been keeping track of the orders to aid in making predictions for what type of meat she tends to prefer for specific styles of food. So this type of data is being tracked by somebody who's thinking, well, she wants Chinese today. So what should I order for her? Should I get her a chicken plate? Should I get her something with beef in it? Should I get her a vegetable plate? That sort of thing. So you track this type of a data so you can make better decisions on certain things. So that we were referring to conditional values. Under the condition she wanted Chinese, what's the probability she wants chicken? That sort of thing. So if we're talking about marginal, what do I think she's feeling like today with regards to type of meat, period? She wants something with beef in it, chicken, or just something that's vegetarian. That would be marginal in this case. Or like, what food style is she feeling today? So is that Tex-Mex, Indian, fast food, Chinese? That's also marginal. So if we just look at every single time that that's occurring, that's also marginal. Okay, so letter A. Give a bar graph showing the marginal distribution of food style for this data. So what I was just talking about. So a bar graph only showing the marginal distribution for food style. And I didn't give myself that much space here, but I get to zoom in. So let's try that. X-axis, which I might need to make that a bit longer. So this is food style, or food type, and style probably better. We're going to have a y-axis for, I get to choose frequency or relative frequency. I'm going to leave it as frequency because I don't want to do extra math. So I'm going to be using those numbers exactly, the 44, 48, 37, 44, and 52. So I notice that the largest number out of all of those is 52. So I'm going to go ahead and say this is out of 60, just to make it simple, round it up. So 60, halfway is 30. And this isn't going to look very precise or very accurate. This is, what would that be, 45 right in between these two, and then 15 right in between these two. So this is going to be very roughly sketched. Our first food style, Tex-Mex. And the first marginal value is 44. So in the margin, that is, so 44. And I'll draw a bar with a height of 44 roughly, somewhere around here. I could shade it in or not, and this day I'm not feeling shading in. So there's that. Indian food. So the marginal value for Indian is 48. So 48 is a little higher. Next category, fast food. Marginal value for that one, 37. So 37 somewhere here. Because I kind of drew a very, very thin or small scale, they're going to look very close to each other. You're not going to see very significant differences between them. If I had enough vertical space to work with and made that a lot taller, you can notice bigger differences between the two. And it's like basically the same thing as zooming in. Next category, Chinese. And I think I made this x-axis long enough so I don't have to be squeezing that. So Chinese, and then Mid-Eastern. And for Chinese, marginal value is 44, which is the same as the first one. Middle Eastern, 52, which is the largest of the bunch. 52 is going to be somewhere up over here. It should be taller than all the other ones, but still not anywhere near where that 60 is at. And that's all they wanted. So here I'm probably going to write frequency for the y-axis because I need to label my axes. Never leave your axes unlabeled. And then I might want to give a title for that. So food style versus frequency, and maybe not, because I feel like the x-axis is good enough for like a title. So what you really need bare minimum are the axes labeled. Title's not always necessary. Letter B, give a relative frequency bar graph. So now they're asking specifically a relative frequency bar graph showing the conditional distribution of meat type for Chinese orders. So going back to earlier, oh crap, she wants Chinese. what type of meat should I order for that? So should it be a chicken plate, a beef plate, or should I get it vegetarian? So what we're going to do here then is we're going to draw or graph the the conditional distribution for protein type or meat type out of just the Chinese orders. So this one I might want to give it's a little easier for coming up with the title. So this is obviously relative frequency here at the top of the y-axis, relative frequency, which I'll abbreviate. Over here, this is meat type. And the title, Chinese orders. So maybe I can go ahead and title this all orders, all food orders, or all lunch orders. Something like that. Okay, so then we do the same thing that we did earlier, except our categories, we only have 3 of them. Beef, chicken, veggie. So beef, chicken, and veggie. And the numbers that I see here, 14, 18, and 12. Problem is they want relative frequency. So what we're doing is we're dividing 14 out of 44 to get that relative frequency. So we go ahead and get a calculator. 14 divided by 44, 0.318 if I round to the nearest place, third place after the decimal. Let's see, 18 out of 44, 0.409, 12 out of 44, 0.273-ish. And those should add up to 1. It looks like they do. So then what I'm doing is I'm plotting those. Now, relative frequency, you have the choice. Leave it as a proportion that way, the way that I have it here, or you can convert it to a percentage, move the decimal place twice to the right, no big deal. So I might want to do that. And I notice the biggest value I see is 40.9%, so I'll make the top 50%. So you're very much okay with leaving those as percentages, or leaving those as a proportion, or making them percentages, no big deal. So this would be what, I think I did this by 5s, 5%, 10%. No, these are not by 5s. These are by 10s, because I don't know how to divide, apparently. So this is 10%, 20%, 30%, 40%. Okay, so the first category, beef, 31.8%. So 31.8% is somewhere around here. And because I kind of botched that already, I'm just going to go ahead and shade that. Chicken, 40.9%. So that's a little higher than 40. Shade that in. Veggie, so vegetarian. Whoops. 0.273, so 27.3%. So that's below 30%, above 20%, closer to 30% though. Somewhere there. Good enough. And that's what they want. So they wanted a relative frequency bar graph showing the conditional distribution of meat type for Chinese orders only. So it's a conditional distribution because we're talking about food orders. And the type of food order is specifically Chinese. So under the condition that she wants to order Chinese food, or under the condition that somebody's going out for Chinese food. So this is the distribution of meat type for just Chinese orders only, under the condition that it's Chinese that's being ordered, as opposed to marginal where it's just a total. It's counts for the total for that one particular variable. So no condition given. Okay, so here are definitions for types of graphs that we can give. So if we're talking about 2 categorical variables, so what we're doing is we're trying to jump to showing the distribution for both variables. So how do I make a 2-dimensional graph? Or how do I make a graph which displays 2-dimensional data, but on a single axis? So 2 ways to do that. One way, side-by-side bar graphs. And we've already seen a side-by-side bar graph where was it? I think it was the previous handout. I don't remember. No, it's not the previous handout. This is the first day's handout. There's a side-by-side bar graph right there. So that's a good example of what a side-by-side bar graph looks like. The next one is a segmented bar graph. Segmented bar graph should be new to us unless you might have seen that in other courses, which I seriously doubt. You definitely have not seen bar graphs in your algebra pre-cal or geometry classes, I'm sure of that. But a segmented bar graph, this one is done with one bar, but each of those bars is going to be cut into segments, each segment corresponding to a category for that one variable that's distributed across that other conditional value for that variable. So it's kind of like a conditional distribution within a marginal distribution. So a side-by-side bar graph shows a comparison of the distributions for each conditional value side by side. So it's like next to each other. Segmented is within the same bar. So we'll see what that looks like in a little bit. We're going to construct an appropriate graphical display that reveals the association between meat type and food style for this data. Then comment on this association for this data. So let's see. It reveals the association between meat type and food style. So we've already seen a side-by-side bar graph before, so I'm going to go with a segmented one. Those are kind of cool. So segmented bar graph. And let me reread what it's asking for. It just says reveals the association between meat type and food style. So then I'm probably going to reread the problem stem to see if there's a particular order I want to do this in. So am I going to show the distribution of meat type per food style, or the other way around? Am I going to show the distribution of food style per meat type? So let's see. So Joe's supervisor is Amy. Amy usually works through lunch. She likes to ask anybody in the office that is already headed out to lunch to pick up some food for her. So if somebody's going out already with the intention of ordering food and getting food, they more than likely already have the type of food or the style of food chosen. So today that person's getting Chinese food, let's say. So then knowing that Amy, so usually the way that goes is like, where are you going? So what is it that you're getting for lunch? Oh, you're going to that place? Can you get me this? So usually it's like, here's the place. You automatically understand what the type of food it is, and then you order the meat type accordingly, or you order specifics accordingly. So I'm going to do this showing the distribution of meat type across all of the food styles. So that's the way that's going to get done. So this will be food style on the x-axis. We're going to have frequency up at the top, and that's not frequency. That would be relative frequency. These are going to be done out of percentages. So it's also better to go with segmented bar graphs, in my opinion, and for the major reason, the statistical reason is that those distributions, those marginal proportions might not all be the same. It's probably not a uniform distribution. So if that's the case, you want to give a distribution that already weights it for the differences or already accounts for the differences in those frequencies. So in a segmented bar graph, let's say, for example, these are what? Food styles, and crap, there's 5 of them. So I got to fit them all. Tex-Mex. The next one was Indian. I'm forgetting something, aren't I? Indian, fast food, Chinese, Mid-Eastern. Indian, fast food, Chinese, and what was the last one? Crap, I keep forgetting. Middle Eastern. Okay, so then what we do is we draw 5 bars of the same height. And what's the height? 100%, or 1 as a proportion. So I'm copying the same big bar with the same height, 100% all the way across. What's going to differ is how these things are segmented, and they're going to be segmented. They're going to have 3 segments. 1 segment for each type of meat choice. So beef, chicken, and then there's veggie. It's not a very comprehensive list. Where's pork at? Okay, so all of these are the same height, 100%. of course, I'm probably going to want to be a bit more specific, show some more grid lines. This is 25%. This is 75%. And do I want to get more specific than that? Probably not. So kind of lazy. So, and let's see, what is this going to require? Oh, you know what this is going to require? So across each of the food types, I need to finish what I started here with the Chinese food one. I need those percentages or proportions all across the board for each of these. So I can already, with the work that I have here, steal these numbers, 0.318, 0.409, and 0.273. So 0.318 is for beef. 0.318 is somewhere here. And I'll leave it unshaded, and that's going to be beef. So my key, unshaded, beef. I'm going to do maybe a horizontal shading scheme for chicken. And then for veggie, we'll go like with a cross diagonal for veggie. So beef is unshaded. Chicken was how much? 40.9%. Added with that 31.8, so that's going to be 72.7%. So 72.7% somewhere around here. And this one was horizontal. I kind of hate the decision to make that horizontal. It's kind of annoying, but I got to deal with it. I'm going to own up. And then the rest of it was diagonal. So then according to our key, what you see is the division of those three categories, but weighted accordingly or appropriately within each food type. And I did that in the wrong one, didn't I? That's in the Tex-Mex one. That's supposed to be in the Chinese one. And I'm going to have to erase that and do that one over. So there we go, I fixed it. And I went ahead and transferred that over to the Chinese one. And what we got to do is we got to do the math for Tex-Mex, Indian, fast food, and Mid-Eastern. So I'm probably going to fast forward to that too. So I'll get started with the Tex-Mex one, and I'll come back once I have all of them. And there we go. So that's the whole table completed. So what I got to do is I got to transfer that over to the segmented bar graph that's in that problem. And that's it for the side-by-side bar graph. So there's an extra little bit of information that we need to give, and it's going to be in the form of a paragraph. So it says construct an appropriate graphical display. We chose a segmented bar graph, not a side-by-side bar graph, segmented. And then comment on this association, the association between meat type and food style. So we want to go by category. So if we're talking about Tex-Mex, so the way that we get this done, if we're talking about the association by meat type, we want to talk in terms of how likely this person is to order a specific meat type given a specific food style. So for Tex-Mex, it looks like she's more likely to order beef and least likely to order vegetarian for Tex-Mex. And then we go by all those categories. Let me write that down. When Tex-Mex is being ordered, this is Amy. Amy is most likely to order beef and least likely to order vegetarian. So then what I'm going to do is I'm going to go ahead and scan the rest of this to see if that's going to be consistent all across the board, or if that's going to differ significantly for some of these other ones. So it looks like Chinese kind of fits the same pattern here. If somebody's ordering Chinese food, it kind of looks like she's most likely to order beef. Actually, not really. That one's a tough one. Is there one here that kind of looks like the case? Fast food, maybe. Fast food looks that way. She's most likely to order beef and least likely to order vegetarian. So I'm going to go ahead and put same goes, roughly, when fast food is ordered. So I'm going to pause again. So I have this one done, and this one done. So Tex-Mex is done. Fast food is done. So let's look at Indian. So Amy is most likely to order, what was it, chicken? If Indian or Mideastern food is ordered, and a bunch of statements like that, which I don't know if I'm going to finish the whole thing. But those are the types of statements that they're looking for when they ask you to comment on the association between these two variables. You come up with some sort of statement for likelihood of fitting in one category with respect to another category for the other variable. So those types of statements, those are the toughest ones. That's very rare on the AP exam. Now, if it does show up in the AP exam, it's usually multiple choice, and there's no multiple choice section this year, but if there was, then they would have given you 5 answer choices all filled out, and you would verify which is the one that's true, or maybe all of them are true except for which one, so then you'd look for the one that's false. So they'd be 5 different statements, and they'd be coming out of that distribution, and you pick out either the true one or the false one depending on what they want. That's most of the times how they get that done. So look at number 2, and number 2 is the last one for this particular problem. Did I have 2 number 2s? No, that's the same problem, number 1, so number 1 was just pretty long. Number 2. So for number 2, each year the Princeton Review conducts surveys of high school students who are applying to college and of parents of college applicants. So students who apply and then parents of those applicants. So the report 2009 College Hopes and Worries Survey Findings, Princeton Review, included a summary of how 12,715 high school students responded to this particular question. Ideally, how far from home would you like the college you attend to be? So students responded by choosing one of the 4 possible distance categories. Also included was a summary of how 3,007 parents of students applying to college responded to the same question. Actually, no, different question. A slightly different question, so it's related. How far from home would you like the college of your child, or the college that your child attends to be? So the accompanying relative frequency table summarizes the student and parent responses. So 2 variables. So the first variable is the sample from which this is taken. So these are 2 populations, students versus parents. And then we have the other variable, which is the ideal distance, their chosen ideal distance. So we have a less than 250, and this is a miles measurement. Between 250 and 500, between 500 and I think that is to 1,000. That was a copy-paste situation, which I don't understand why that would have been a copy-paste situation, but that should be 1,000. And then it's greater than 1,000. So less than 250, between 250 and 500, between 500 and 1,000, and then greater than 1,000. So these are people who really hate each other, like the kids and the parents not liking each other. They want them to be as far away from each other as possible. So let's see. Construct a side-by-side bar graph to compare responses regarding ideal distances for each of the 2 samples. So side-by-side bar graph. So they're not giving me a choice here. Now they're telling me do a side-by-side bar graph for each of these 2 samples. So then, if it's side-by-side, we can do numbers-wise, or we can make that a relative frequency. So they give me freedom to choose if it's a relative frequency or just a regular frequency. And I think I'm just going to go with regular frequency, because relative frequency requires division, and I'm kind of not wanting to divide and stuff like that. So y-axis, so I can do a better job. This is frequency. X-axis, distance. And it's a distance category. So this is less than 250, 250 to 500. This is in miles. 500 to 1,000, and then greater than 1,000. So 4 categories. Within each of these categories, though, because it's 2-dimensional, we want 2 bars per category. So per category, 2 bars, one of them for students, one for parents. So in this case, I normally go with shaded versus unshaded. And what's the largest number I see total? Like, what is the absolute largest number in that sea of numbers? 4450 is the largest number, disregarding the totals, that is. So 4450. So I'm going to go ahead and round that up to 5,000. And then we're going to mark these off by thousands. Actually, no, that's kind of bad, because a lot of these are... Actually, no. That's perfectly fine. So I'm going to go ahead and stick with that. And these should be a little further apart from each other. So 1, 2, 3, 4, and 5. And that's not too bad unless I fix... If I fix this one, and maybe this one. So that's not too bad. So that's somewhat accurate. So each of these are thousands, and then 4,000. And we can keep it at that. Maybe halfway we have the 500 marks. So 500, 1,500, 2,500, 3,500, 4,500. And yeah, so then for the first category, the 250, well, less than 250, we have 4,450 for students. So 4,450 is really close to that 4,500 mark. So I have a bar here. And then the corresponding one for parents would be 1,594. And 1,594, that's significantly less than 4,450. I don't know why that keeps zooming out like that. So 1,594, very close to the 1,500. I'm going to shade in the smaller one because I want less shading. And the parents one looks like it's going to be a lot smaller for that one. Yeah, because the sample size for parents was a lot smaller. So then between 250, 500, 3942. So 3942, 3942. I can edit. 3942, 902. Somewhere around here. And that one's going to be shaded in this way. Something like this. 500 to 1,000, that was a typo. That should be 1,000. So that's 2416, so close to the 2,500 mark. Somewhere around here, so I'm just eyeballing it. And the 331. 331 is somewhere way down here. And that one's shaded in. Less than 1,000. 1907. 1907 is very close to the 2,000 mark, somewhere around here. And then for parents, 180 is very small, down here. And there's a side-by-side bar graph. Now, what does a side-by-side bar graph allow us to do? Well, one, it allows us to do what letter B is asking for, differences and similarities. That's by category. So one thing it allows us to do is make comparisons by category. And this also kind of shows why a side-by-side bar graph could be bad. In this case, since if you look at the sample sizes, these sample sizes differ significantly, then you're going to notice that this one is going to be a lot smaller than this one. And that's a lot of it has to do with because of the differences in the sample sizes. So obviously these are going to be way smaller than these. All right, so I don't know if I can make accurate comparisons category by category that way, but there's general statements to be made. So as distance goes up, generally both of these for either population group are decreasing. So as distance increases or distance category increases, then the number of responses or the percentage of responses, also true, is decreasing with distance as it increases. So and that's true for both. So that's going to be counted as a similarity between the two. So as distance goes up, generally the number of responses out of the total goes down. So that's a similarity. So I'm going to go ahead and start that already. So generally, as distance from home, or distance between home and the campus that they are enrolled in increases. So as that distance increases, the percentage of, and it's hard to tell because I didn't graph percentage. Maybe what I should have done was graphed relative frequency instead. That's what should have been graphed, relative frequency instead, not frequency. So if I had changed that to relative frequency and relative frequency by distance category, that would have been a more appropriate graph. So this is more of an inappropriate graph. So the percentage of responses out of the sample size decreases. That's a similarity. And when they say describe the differences and similarities between, if this were an AP exam, you're good with one of each. One difference, one similarity. So then, for the difference, that's probably where a relative frequency distribution would have been a lot better, or a relative frequency bar graph would have been better. Once those are changed to percentages, then we can accurately compare the distance between these two. So we would have talked about where is this widest, where's the biggest difference. Here we can't really tell because these are counts, and I don't know if the difference between them has to do with the sample size or if it's because there's actually a difference of opinion with respect to whether they're a student or a parent. So we don't really know. So I'm going to leave that part blank for the differences, but definitely we have that similarity that responses decrease as distance increases. And then we'll go ahead and stop here for this handout, and that's going to be the end for this first half of the chi-square stuff. So that's the last handout. Expect a homework assignment that these will be posted with. So I'm going to post the videos and the homework assignment all together, most likely in the same spot under Unit 10. So we're on the 10th unit already, chi-square testing. So there's a Unit 11 for linear regression, t-testing, and that's our last one.